and it's fixed. And it's really obviously present. Okay? Now, combined with the fixed sampling plan, it means we're sampling all of these different points each time. Right? So our within group standard deviation is going to be inflated by this kind of phenomenon, this fixed profile each time, right? Just think about it. If you were calculating a range each time and not a standard deviation, you'd almost often be taking a difference between here and here. Right? Those two values most times define your range. And of course, your limit then is going to end up being much too large. Now, purists would suggest, well, fix this, right? Why are you letting that happen? Well, it's not so easy, right? It might require a next generation tool, right? That might be a tool design issue, right? It actually might even be desirable. They might even plan the process to be like that because they got a downstream process that has an offsetting dome effect, okay? So that's potentially possible as well. So you might want to leave it there, right? In any event, the traditional upper control limit for this chart, which we calculated at 27 something, probability of generating a signal, even with a doubling of the actual within wafer standard deviation, is about, and detecting it, is about 1 in 1.1 million. It's never going to find it. So what might we do? If we have to accept that this fixed profile is part of the process, what could we do? Well, there is a way to handle it, right? What this organization chose to do was establish a new and rather arbitrary rule that would signal if 2 or more within wafer results were outside of specs. Okay? All right, kind of an ad hoc rule. Easy to execute, but it brings specifications directly into the control process. Probably not a desirable thing. Okay? And it's difficult to assess its relative effectiveness. It can be done, but it's not easy. There is a statistically valid way to do this. It involves a non-central chi-square distribution, which utilizes the profile to estimate the non-centrality parameter. They're not going to go into the details, but there is a way to do it, right? And if you do it using the statistically valid approach, you can find that the control limit that you would find that way would be not 27.4, it'd be 17.1, right? And if you look at the average run length curve for that, well, it's clearly much lower. For a doubling of the ratio of sigma, you can pick it up in about 6 or 7 observations, whereas with the other limit, it's going to take about 1 in 1.1 million. Not going to work. Now, what about the rule that they decided 2 out of the observations need to be out of spec? Well, turns out you can find the average run length for it. It's not easy, it's not trivial, but it can be done. And it looks something like this. It's actually better down for smaller shifts here. And it has a lower false signal rate than this statistically valid approach, but it's pretty flat. You can actually change the statistically valid approach to get a false signal rate that's similar by just increasing the limit slightly to 17.9 approximately. And you can see that it still is far superior to this approach. Okay, so some considerations. You need to decide if variation is something you really want to control. Right? It's something you really want to control. Right? And control means if you get a signal on that variation chart, you're going to do something about it on the process. Right? That's what control. You're going to try to go act on the process. Or is it something you're just going to monitor? Right? Most of the time, my experience is we do monitoring, not controlling this, because it's not clear what to do with variation lines. Sometimes there's tool shut down that do investigation, and there are things that can be done. So the question to ask is action really going to be taken on the process when you get a signal for this variation statistic? If it is, fine, you're going to control it. Right? If it's not, you got to ask yourself, is a control chart really necessary? Maybe, maybe not. You might treat it as a less than critical parameter, set wide monitor limits on it if you decide not to control it. You know, if you're only going to hold product, remember, holding product is not taking action on the process, it's taking action on the product, a finite amount of product. But if you're going to involve it in a disposition decision, then you might want to consider maybe tolerance limit type things, using disposition limits that involve that standard deviation. Another way to separate your disposition procedure from your control procedure, we probably won't include that. know the process well enough to realize what the statistic is actually representing. Is it indeed consistent with the model, a single variance component, within group component, or is there something else going on, like this systematic profile? You know, if you've got, once you've figured out what's going on, use the control plans. The normal control plan's fine if this model is reasonable, right? Now, what did Bach say about models? Anybody remember? You know. All models are wrong. But, there's George Joinder, he said, some are more useful than others. Okay? So, if you find this one's a more useful model than this one, then use the standard approach. Right? If it's not, then use an approach that's appropriate for the situation. Right? Now remember, when you're doing these charts, this is an additional control chart. Right? So it has a false signal rate as well. Right? You've added another chart. Right? So when we were talking about 50,000 to a million, if we're running X bar and R charts on all of those, you just doubled it. Just doubled your rate of false signals as well, potentially. Okay? So, again, when you do this, you want to try to balance your false signal rate with the sensitivity. Again, appropriate ARL curves might be helpful. All right, so we have organizations that, one, right, in order to align with advice they got from customers and literature and numerous experts, they created an SBC system, an automated system, that actually defeated the purpose of SBC. Right? It allowed its process to wander off and it distracted most of the time. Okay? They were trying to do the right thing. In order to determine specifications that related to functionality, right? They were looking at it as yield. They produced specifications that were seriously underestimated the true magnitude of the variation of the product units. Right? Trying to do the right thing. And then, in order to routinely assess process variation, they followed the commonly communicated approach. Of course, it generated meaningless, ineffective control charts. And then, of course, the approach they took to kind of rectify it, they were smart enough to realize it's not doing anything for us, was suboptimal as well. Right? They had good intentions. Right? So is there a common theme in why these well-intentioned efforts produce less than desirable outcomes? I don't know, but this is the conclusion I came to. Maybe. I'm too ignorant to know. Okay? I don't know what the common theme is. But reality has a way of impacting even the most well-intentioned plans. Right? What do they say? If you want to make God laugh, make plans. Right? And in previously unforeseen ways when you're trying to implement them. So what do organizations have to be able to do? They need to be willing to adapt, innovate, change course, and yes, even sometimes just punt. Right? Hey, this isn't working, and move on. Right? If they're willing to do that, then they may indeed avoid their own